So in order to understand the current response and output voltage, in the case of buck converter, for a discontinuous conduction mode, which we say that the inductance is now less than the critical value of inductance, and now we know that for that case, the current is going to be discontinuous. So the total time period is basically T here, and you have turned on your switch up to dt, and the current is hitting 0 much before, let's call that as beta t. So now, if you want to assess this performance of buck converter here, now we know that we are drawing a current through the inductor. Now, if you look at the inductor conditions, when your switch is on, the inductor is having a source voltage on the beginning side and the load voltage on the other side. So the voltage across the inductance is Vs minus V0. Similarly, when the switch is off, if you don't have the switches on, then the inductor will experience only output voltage. The input side voltage is 0. That is, input side voltage of the inductor is 0, output side is V0. That is, inductor voltage is now 0 minus V0, which is minus V0 itself. So during turn on of the switch, the voltage across the inductor is Vs minus V0. The during turn off condition of the switch, the voltage across inductor is just minus V0. Now, if you want to know the rate at which the inductor current is changing, which is dIL upon dt, it is now going to be VL by L. That's a very fundamental equation. So what is VL for us during turn on condition is Vs minus V0 upon L. Now similarly, the dIL upon dt here is minus V0 upon L. That is nothing but the rate at which your current is changing during turn on time of the switch, the rate at which your current is changing during turn off time of the switch. So the rate at which your current is changing is nothing but the slope of this current. Now you say that the slope here is Vs minus V0 upon L. Again, the slope during turn off, that is minus V0 upon the value of inductance. So now you know the slope at which the current is changing. Then if you want to get the expression for the current, which is I of t, so I of t is going to be slope multiplied by time itself. That is Vs minus V0 upon L multiplied by t. That's what is the current expression during turn on condition. Now what will be the current expression during turn off? That is here. That current is, that is I of t, you can say IL of t. It is not starting from 0, but it is starting from I max and it is reducing from there. That's what we observe. So consider that this value is I max for us. So it is I max starting from there, and it is having a slope of minus V0 by L. So now you can say that it is minus V0 by L, that is slope. And the time is basically having a delay because your current here, this current is not starting from 0 time, it is starting with an offset of dt. That is the waveform expression. So now you have a delay of dt, so now you say that it is t minus dt. This is an expression for the output inductor current when your switch is turned off. So now from these two, if you want to get the expression for the maximum current and consider that the maximum is same in both the cases, then you will be able to get the relationship between the input voltage and output voltage. Now for this turn on condition, during the turn on, if you say that okay, my time t is equal to dt, means at your time t is equal to dt, at this time you are having your current to be maximum. So when your time t is equal to dt, you can write down that I max is equal to Vs minus V0 upon inductance multiplied by dt. So this is an expression for maximum current. Now if you want to get expression for the maximum current from here, you also substitute the boundary condition that at time t is equal to beta t, my I of t or IL of t is equal to 0. If you substitute that boundary condition, that is IL of t is 0, that is I max minus V naught by L t minus dt. This is equal to 0 when your time t is equal to beta t. So now instead of time t, you substitute that beta t there. Then this gives you another alternate expression for the maximum current there, which is equal to V naught upon L multiplied by beta minus d multiplied by t. So that's an expression for Imax. So this is your first way of getting your Imax. This is your second way of getting your Imax. Now both are same. The maximum current is same in both the cases. So you end up with the maximum current when you turn on your switch, and you start from the maximum current when you turn off your switch. So knowing that fact, if you equate these two, then you will be able to say that, okay, my Vs minus V naught upon L multiplied by dt is equal to V naught upon L beta minus d multiplied by t. So now if you solve this, you will be able to get an expression that V naught is d upon beta multiplied by Vs. This is what you get if you simplify that equation. So now what do you get is your output voltage is d upon beta times of Vs. In the previous case, when you had a continuous conduction mode, there you said that, okay, my V naught is d times of Vs. So this is the old one. And now what are we getting is that the output voltage is d upon beta times of Vs. It's a different one. This is for a discontinuous conduction mode. Now what is happening in the case of discontinuous conduction mode? Means the expression that we had earlier to get an output voltage that is d times of Vs is no longer valid if you have selected a very low value of inductance, which is causing discontinuous conduction mode of current. How much will be the output voltage is d upon beta times of Vs. So there is a factor called beta coming into picture now. Now you know that your current is not becoming 0 beyond t. Means beta t is always less than t. If beta t is always less than t, means if you say that my beta t is always less than t, you're in a way telling that beta is always less than 1. If beta is always less than 1, you are dividing the dVs with a factor which is less than 1, which is indicating that V naught is always going to be higher than the V naught that you would have got with d times of Vs. So, in a way you're telling that V naught in discontinuous conduction mode is 1 by beta times of V naught in continuous conduction mode. Since the value of beta is less than 1 always, you always say that the V naught in the case of discontinuous conduction mode is always greater than the voltage in the case of continuous conduction mode. So you will be getting more average output voltage, but the problem will be your output current is discontinuous. Your inductor current is discontinuous. That's what is happening when you choose low values of inductances and your current ripple is very high. So knowing that this is the expression, now how do you know the output voltage? You will choose your values of d, but how much will be the value of beta? How do you get to know the value of beta so that you will be able to calculate what is your output voltage if you have a discontinuous conduction mode of current?